astrophotography, and you can see from the subtitle, photographing the night sky, but ideally without ridiculously expensive equipment, though that is an option and I'll mention that in passing. So what do you need for astrophotography? Well, you can start simple. You can just have a camera and a tripod. That's pretty much the sort of the basics. You can, if you wish, start buying equipment, and you can think about buying telescopes and the mounts that allow you to mount the telescope and track the sky. And you can think about all sorts of specialisms like particular cameras that do particular jobs. And I'll talk about star trackers. Then I'll show some of my images just to show them off. And what do you need? Well, you don't need the darkest of skies to do astrophotography, but it certainly helps. So I'll show you a few pictures that I've taken from Africa to give you a taste of what can be done. So we'll start with just a camera and a tripod. So effectively, if you've already got a camera and a tripod, this is, if you like, zero cost astrophotography. And this is one of the earliest pictures I took some years ago now. You can see from the details right at the bottom of the screen, this was not taken with a digital camera, so that tells you how old it was. This is getting on for a couple of decades ago or so. Just putting a camera on a tripod, pointing it at the sky. In this particular case, I was on holiday, looking at the pyramids in Egypt and visiting Jordan. And this was in the middle of nowhere, taking a picture of the sky with a few minutes exposure and a wide-angle lens. There's Polaris in the middle of the image, not moving, while all the other stars, after a few minutes of movement, have trailed slightly around Polaris. And that classic star trail is just the easiest image to take. If you wanted to expose for longer than a few minutes, well, from the UK you might suffer from light pollution, but if you get to nice dark skies, you can expose for much longer. With a digital camera, you're not limited to taking one long exposure. You can take a series of shorter exposures. For instance, here I've taken a whole series of 30-second exposures, and then once I got home, added them all together. So this is equivalent to a 6-hour exposure. You can tell that by looking at the length of the star trails. Each star trail is approximately 1/4 of an arc, so 1/4 of a day. So that's 6 hours during the night. It almost looks like daylight because we've got blue sky and what looks like daylight foreground. That's simply because it was taken during a full moon, and the full moon is illuminating the observatory domes and the grass, and the full moon is making the sky rather less than black and giving you the blue tinge. But again, even from the UK, you can take very nice star trails. If you have clear skies for a few hours, there's no reason why you can't take something similar to that. Some of astrophotography is just serendipitous. A few years ago, a comet happened to go by that was actually large enough, the actual coma, the actual head of the comet, expanded to the point that where it was easily seen, not in telescopes, but in just a telephoto lens in this case. Some of the images I'm showing you are wide-angle shots of the sky. Some of them are telephoto lenses. I've always put the focal length at the bottom just so you can refer back. So in this particular case, this was a telephoto lens on a camera, on a tripod, pointing into the sky and taking, again, a series of shortish exposures. So in this particular case, the camera wasn't tracking the sky. I was just keeping the exposures short enough that the stars hardly moved during the, in this case, 30-second exposures. And again, being in the right place at the right time. If you're lucky enough to be far enough north or south of the equator, somewhere close to the Arctic or Antarctic Circle, then you can catch the northern or southern lights, in this case the aurora borealis, as seen from Iceland. And again, this is on slide film not particularly sensitive compared to modern cameras, so I had to expose for quite a long time. I'm not sure if it was 300 seconds or not, because of course you don't get the information digitally stamped onto the images. So I'm trying to remember how long this particular exposure was. So some of the detail in the auroral curtains have been blurred out by a long exposure. I would love to go back to Iceland with a digital camera where the exposures can be shorter and then you get more detail in the auroral curtains. For those of you who know about the night sky, perhaps you recognise over on the left-hand side there the constellation of Orion just peeking into the field of view, and the Pleiades star cluster, the Seven Sisters, in the middle there, almost getting drowned out by the bright green of the auroral display. In this particular case, we had a few hours of display and the aurora covered almost the entire sky. Quite spectacular. And again, right place, right time. The classic example of that is a solar eclipse. If you ever get the opportunity to witness a total eclipse of the sun, it is absolutely awesome in the true sense of the word rather than in the American sense of the word. Standing in the moon's shadow and catching the instant at which the moon just covers the sun, in which case you then see the beautiful solar corona, is absolutely amazing. I had that opportunity. Friends and I went to the Sahara Desert in 2006 to see that particular eclipse. So what can you do in terms of buying stuff? If you wanted to get seriously into astrophotography, if you're not happy with simply, I've got a camera, I've got a tripod, then how much money do you need to spend on astronomical gear? Well, there is pretty much no limit. The Hubble Space Telescope is currently having difficulty with its computers, and so who knows, at some point NASA might give up on it and put it on eBay. So watch out, because there might be a bargain up for grabs in the next few months or possibly the next year or two. If you have got $1 billion to spare, then you can produce images like that, the beautiful M51 Whirlpool galaxy, and on the right, the famous Pillars of Creation. That particular image was taken not in natural colours of red, green and blue, but very specific narrowband colours using filters that only let through the light of hydrogen or the light of sulphur or the light of oxygen in this particular case. And then those three images have been combined in a particular way that Hubble call the Hubble palette. It's their particular choice of colours in order to bring out the hydrogen, the oxygen, the sulphur as clearly as possible. If you don't have $1 billion, if you only have 100 million to spare, then you can buy yourself a 747 and put a telescope in the back of it. That's what's done in this particular observatory. This is an infrared telescope that NASA use. And infrared telescopes, the atmosphere absorbs a lot of infrared depending on which wavelength you're trying to observe in. And so you want to get as high as possible. And as high as possible, even high mountains are not high enough. You really want to get above most of the atmosphere. So flying an infrared telescope in a 747 makes perfect sense, but perhaps beyond your budget. So let's come down to a mere £1 million or so. There are telescopes like the Liverpool telescope, for instance, still the world's largest robotic telescope. It was when it was built, and I believe it still is the world's largest robotic telescope. Bear in mind that you don't have to buy a robotic telescope. You could, if you wish, just rent one. There are lots of robotic telescopes around the world, and if you want to simply use one for an hour or two, or perhaps even just a few minutes, you can effectively buy time on telescopes. Whether you regard that as a really good way of doing astronomy, or whether you regard that as cheating, well, I'll let you judge that. But the Liverpool telescope can be used to take images. This one I took back in 2012, and there's the Pillars of Creation, in this case not using the Hubble set of filters, but here just using red, green and blue filters. And this reminds you that most of the universe lights up in the colours of hydrogen, in other words red. So there is a particular line in hydrogen at about 650 nanometers at the red end of the spectrum, and hence a lot of nebula just look red if you take them in natural colour, which is why Hubble and other people choose to use narrowband filters at the hydrogen or oxygen or sulphur or other element lines in order to pick out the chemistry more clearly. And here's a picture of M51, again to compare with the earlier picture from the Hubble Space Telescope. Galaxies tend to be broadband, they emit across the whole spectrum, unlike nebula, which tend to emit at specific wavelengths corresponding to the gases in the nebula. That all of the stars in a galaxy will emit across the visible spectrum, and hence the image appears to be relatively colourless, except for particular dots that might be in there. In this case, this was a monochrome image taken on the Liverpool telescope. If we come down to more sensible budgets, you can see I've indicated here a few hundred to tens of thousands of pounds, because amateur telescopes can indeed cost you almost anything. I would argue that anything less than a couple of £100 doesn't buy you a very good telescope. If you're seriously thinking about a telescope to buy, you have to invest at least a few £100, and probably closer to £500 would be more sensible. But there's almost no upper limit. The telescope you can see in the foreground here costs approximately £25,000. So you can go obviously somewhere between those hard limits. There are lots of manufacturers. Meade is one, that's an American manufacturer of telescopes, which will provide telescopes from of order £1,000 up to quite a few £1,000s. So you don't have to go overboard, but some people are quite happy to invest their life savings in their hobby. And having taken a perfectly good telescope like the one on the left, some people then decide to add accessories. I mean, what are you going to do? You buy a telescope. Some people don't think it's a complete telescope until you've bolted on a few hundred kilograms of other things that you then get for your birthday or for Christmas or whatever. In this case, there's a motorized focuser, there's a camera, there's all sorts of bits and pieces added on to this particular telescope to make it more functional, depending on your definition of what you want to do with the telescope. When you're thinking about buying a telescope, if you wanted to do astrophotography, part of what you have to think about is the quality of the telescope you're buying, the optical quality. Is it diffraction limited or does it have aberrations? But many people would argue you have to spend at least as much thought and possibly as least as much money thinking about what the telescope is mounted on. If you want to image something by tracking the sky as the Earth rotates in order to follow and not blur the images that you're obtaining, then the precision and the sturdiness of the mount is just as important as the optical quality of the telescope. There is no point in having a superb optical quality telescope if it's bouncing around all over the place and you can't point it where you want to point it. So yes, it is important to have a nice, sturdy and ideally precision mounting. But I'll let you decide whether that particular mounting, for instance, is worth £10,000. Before you think about what it's mounted on, before you think about the optics of the telescope you want to put on that equatorial mount, would you want to invest £10,000 in that? When you're getting to the sort of costs which I think of as being the cost of a house, which it was in my early days, then I think it's getting a bit silly. Where are you going to put a telescope if you did have one? Well, it'd be nice to put it in an observatory dome. That's Palomar Mountain in California. When I was a PhD student, I visited that particular site to go and look at the world's largest telescope, the Hale 200-inch telescope, which is the subject of a completely different talk if you're interested. But I visited that particular dome and the telescope inside in 1982. That's me with slightly longer hair, but probably the same shirt I've still got. And I visited it and I said to myself, that is a fantastic telescope, that's a fantastic observatory. When I'm an adult, I'm going to buy a house with a garden big enough to put an observatory like that in the bottom of the garden. Okay, a few years later I had to downsize my aspirations somewhat, and I ended up with a B&Q shed that I modified into a back garden observatory. That's now somewhat more overgrown. These trees that you can see in the background are now about 10 times higher, and that's starting to block my sky. Well, it was starting to block my sky years ago, so it's unfortunately more difficult to use. But inside the observatory, the roof simply hinged back so that I could see the sky, and there's a telescope that I bought some years ago. You can tell that's a very old picture, about 20 years old, for two reasons. A, the observatory is very clean, so clearly that was a picture I took immediately after I built it. And secondly, you can see the laptop in the background there is more like a house brick than the thin sliver of paper that you get with laptops these days. So again, you can date it from those two things. But with a modest-sized telescope, you can get some superb images simply just watching the moon and looking at the sort of detail you can see in the craters in the mountains as the sun's shadow changes. That alone can be absolutely fascinating. And when I got my telescope, I thought I would give a try at using video. Rather than bolting a camera onto the telescope, I thought, what can you get if you take a video camera? So this is an old-fashioned video camera. Remember camcorders? Some of you will, some of you won't. Camcorders, these very large bulky items in which a tape would record what the video was seeing. In this particular case, I brought the video camera up to the telescope. It wasn't physically coupled to the telescope. I pointed the video camera down the barrel of down the eyepiece of the telescope and obtained these images of Saturn. Very grainy, very bouncy. The Earth's turbulence, Earth's atmosphere turbulence is making it bounce around all over the place. But if you capture a video, what you've effectively got is something like 10 frames or maybe 20 frames per second. If you record a minute's worth of video, what you've actually got is hundreds of images of the object of interest. And just like you would take a spectrum by taking a scan multiple times and averaging them to reduce the relative noise, to improve the signal to noise, it's the same idea with images. In this particular case, you can look at all the images or get a computer code to look at the quality of each image, throw away the ones that are really blurred, keep the ones that look reasonably good, and add them all together so that you end up with a reasonably nice still image taken from all of the video frames. Now we can see a bit of detail on the surface of Saturn. We can see that the rings are not just one ring but multiple rings, and we can see different coloration within the rings, and we can very clearly see the shadow of the globe of Saturn on the rings, because the sun is effectively over my right shoulder, causing a shadow onto the rings themselves. So a very crude way of doing astrophotography, but when you're dealing with things like planets, because they produce such a small angle on the sky, you do need the sort of magnification that only a telescope can achieve. But there's plenty of way of doing astrophotography without the need of the magnification of a telescope. Let's just have a think about whether or not it's worth buying specialist cameras, and then think about star trackers. If you're dealing with monochromatic film or a monochromatic CCD chip, strictly speaking, all CCD chips are monochromatic in the sense that they are not sensitive to different wavelengths of light. If light goes through a lens or a mirror system to then image onto a chip or a piece of film, you can obtain colour images by putting coloured filters in front of the sensor, or indeed in front of the lens if you so wished. With a camera lens you can put filters on the front of the lens. But with astro imaging, what people tend to do is to put filters before the sensor, and hence take a monochromatic picture in red light, and a monochromatic picture in green light, and a monochromatic picture in blue light, and then afterwards combine them together into a colour image, which was precisely how colour imaging was done before the days, for instance, of colour film, where very cleverly they had different emulsion layers within the colour film and different filters between the different colour sensitive layers, and so there were not just 3 but there were probably 6 or 7 or 8 different layers of the film, in order that one layer produced the blue image, one produced the green image, one produced the red image. With CCDs, because the individual chips are not colour sensitive, you have to put filters in front of the pixels. And a standard way of doing that, if we blow up what's going on in the middle of a colour chip, we find that we get what's called a Bayer grid. In other words, each pixel has its own colour filter, and it obviously changes and alternates from red to green to blue. You might notice that when you deconvolve those and separate them out, you end up with a red image produced by the red pixels, a green image from the green, a blue image from the blue, and notice that you have gaps. So the first thing that the computer in your camera has to do is interpolate to fill in those gaps to give you a full colour image. You might also notice there are twice as many green pixels as there are red and blue, simply because 3 doesn't fit neatly into a 2x2 square unless you double up the green. That's actually quite handy, because for daylight photography, given that our eyes are more sensitive to green than they are to red and blue, taking an image in which you have more information in the green channel is actually quite handy. That gives you, generally speaking, better signal to noise when you're taking pictures in daylight. But if you're taking astronomical images and you're picking up information directly from the chip, you have to bear in mind which pixel corresponds to which colour, so that you can combine the information correctly into a colour image when you're done. If you wanted to, you can pay, again, almost as much as you like for an astronomical camera, one that's designed for astro imaging that would then, if you like, replace the eyepiece on a telescope. So you can start from a couple of £100 or so for a colour sensor. In other words, what I've just shown, a monochromatic sensor with a Bayer grid of colour filters in front of it. If you wanted higher resolution and perhaps lower noise, you can go up to paying thousands of pounds for a colour camera. And for the diehards, it's still possible to buy mono cameras. In fact, a lot of people simply prefer mono cameras. They might cost you the same amount of money. The catch is you then think about filters. And it is not uncommon for people to have filter wheels with a number of different filters, and it's driven by a stepper motor. So before you instruct the camera to take an image from your laptop or computer, whatever it is you're using, you would instruct the filter wheel to dial up the relevant filter that you wanted. You might take a red filter and then take a 1 minute exposure, and then change to a blue filter and then take a 1 minute exposure. Then the green filter, another 1 minute exposure. But the real power comes in the fact that your choice of filters could be not simply red, green and blue, but your choice of filters could be a filter explicitly designed for hydrogen, a filter for oxygen, a filter for sulfur. If your object emits only at those lines, then picking out those lines and throwing away the rest of the electromagnetic spectrum effectively gets rid of light pollution and only lets through the light from the astronomical image itself. It effectively improves your signal to noise. But you can see the expense is financial and complexity compared to a one-shot colour camera where you take a picture and all the colours are taken at once. So if you already have an SLR camera or a bridge camera like I do, and I guess Connor does, if you already have a camera and are using that for photography of whatever objects interest you, then why not just use that camera rather than think about spending more money on more specialist astronomical gear? And I particularly believe that star trackers are wonderful devices that allow you to take equipment you've already got, a camera and a wide-angle lens, or a camera and a telephoto lens, and then you can apply them to astrophotography. A star tracker you can build yourself if you so wish. This is the second star tracker I ever made. I made one when I was a college student, which was terrible. This one is a little bit better, and this one I've used for quite a few years. I built it somewhere around 2006, and I've used it from 2007 for quite a few years. It's simply a barn door tracker. It's two slabs on a hinge, which are opened by a drive that is simply motorized. I used a simple DC motor. People sometimes use Arduinos or stepper motors or whatever. It can be done a whole range of different ways, but I would argue that a tracker can be built for 20 quid or so using a few bits of aluminium, in my case a potentiometer, a couple of batteries, a motor and a gearbox. After using that for quite a few years, I changed to using a commercial device. This particular one is made by Ioptron. You can see it's a little box. It's effectively just a box with a motor inside it, and in this particular case it has a polar alignment telescope here to make sure that you're lined up with the Earth's axis. If you're trying to follow the stars, then you need to rotate the camera at 1 revolution per day, strictly 1 revolution every 23 hours 56 minutes, because that's how long a sidereal day is. You want that particular speed, and you want its axis of rotation to be parallel with the Earth's axis, such that as the Earth spins one way, the tracker moves the camera in the opposite direction and effectively holds the camera still as the Earth turns. That particular device, this particular device I'm using, happens to be more precise than the one I built for myself some years earlier, but as Connor has already found, they cost at least a couple of £100 or so, and whether that's worth it or not, or whether you prefer to build one for yourself, that depends on how deep your pockets are and whether or not you've got the patience to build one yourself rather than just go out and buy one. That particular tracker, I think, is now obsolete. I bought that one in 2015, and that's the one I still use, mainly because A, it does its job, and B, it's small enough that I can take it on holiday. So if I go on safari in Africa and I want to take pictures of the night sky, apart from the camera, which I'm already taking anyway, and the tripod, which I'm already taking anyway, that's the only extra bit of luggage I need in order to do astrophotography. So here you can see other people have mounted their cameras, whether they be bridge cameras, DSLR cameras, it really doesn't matter. It doesn't really matter whether it's wide-angle lenses or medium or longer telephoto lenses. You can add a kilogram or two onto these devices quite happily. I've also used the camera and lens that I use for safari. That's my lens of choice, telephoto-wise, a 300mm telephoto lens. The lens itself is an extra 750 grams or so on top of the weight of the camera body itself, and the trackers have no problem at all moving that camera around, as you can see on the left-hand side there. That's what's inside typically these trackers. There's not an awful lot to them. They are effectively just a little bit of electronics, a small motor and gearbox designed to run, the motor runs quite fast, but of course the final drive wants to be 1 revolution in 23 hours 56 minutes. So it doesn't have to be a high torque motor because it's geared down so much you can move even a relatively heavy object with a very small motor. What you're paying for is the precision of the speed at which it runs and the precision of the actual drive itself. In other words, no backlash and no rattle, and that is guaranteed to be parallel to the polar scope, which goes through this little hole here, so that when you've lined up the polar axis, you know that your camera is tracking in the right direction. So let's have a look at some of the images I've taken with my camera. I've already shown you a couple of images I've taken through the telescope, the Moon and Saturn. Everything hereafter is my camera taken with a star tracker. So just an example, because again I think Connor asked this question in terms of what you do with image processing. One thing to bear in mind is the image you get off the camera never looks as good as the final images you see posted on web pages, etc. This is a picture of the sky taken with a 300mm lens, and it's a part of Cygnus High in the summer months of the UK. A single raw image shows you almost nothing apart from a few dots and a few stars. If you squint, depending on your screen, you might see the hint of a nebula in the middle of this image. But again, coming back to the whole argument of signal to noise, if you take a single exposure, you might not see much. If you take a whole set of exposures and add them together, you're improving the signal to noise. So by taking those images, it might be the images aren't perfectly aligned with each other, but Image SXM basically checks where the stars are and makes sure that the images are perfectly aligned before adding them all up, to make sure that all of the signal effectively reinforces and all of the noise tends to cancel each other out. So by stacking together, by registering automatically and then adding up 20 of these images, you can start to see more information coming out. And after you've stacked these images, if you wish, you can then, in your image editing software of choice, you can then tweak the colours and the contrast to try and bring out just a little more detail in that nebula. So you have to remember that everything that's on the right there, all the information in there, is in the image on the left. It's just very difficult to see and somewhat more shrouded in noise. But effectively, image processing is about stacking to improve the signal to noise and then tweaking so that your eye is then more readily seeing the information that's in there, the colours and the contrast that's in there. So that's implicitly what I do for every image I take a series of short exposures and add them together to give you the result. This is the result of a star party in the UK. I went with some friends down into Herefordshire, where we spent a couple of nights over a weekend taking images or just looking at the sky with binoculars. Here on a tracker, I've taken 3 objects: the Pleiades star cluster on the left, the Andromeda galaxy centre bottom, and in the top right there's a nebula which is the result of a star that went supernova some, I don't know, 5,000 years ago or something. And what you're seeing is the shell of gas that came off this supernova. The supernova has faded away and there's no way you can identify which star it was, but you can see clear, distinct shells of gas that have been released many thousands of years ago. And even though this was a one-shot camera just taken with standard red, green, blue Bayer filtering on the CCD, you can already see that this particular object seems to be glowing mainly in the red and mainly in the blue to cyan colour. That's because this particular object is glowing in the light of hydrogen and oxygen. And if you had chosen to buy a monochromatic camera and look at it with those particular filters, then the nebula would pop out even more against the background of stars, more so than I can do with my colour camera here. But these three images just show you what you can do with a camera on a star tracker, as long as you get away from the worst of light pollution that cities can offer. This was a planetary nebula, a star that's blown off the outer atmosphere. So you're seeing a few slightly blobby stars here. The seeing wasn't fantastic. This object is low down in the south during the summer, but you can quite clearly see this particular shell of gas that's been blown off by this particular star. I like this particular image because if we compare it with a Hubble image, okay, the Hubble image, I'll grant you, is better. Yes, it's higher resolution. There is more detail in the Hubble image than there is in my image. But my image cost a few £100. The Hubble image cost, I don't know how many $billion. So, yep, okay, you can never compete with the wonderful images that you see on the internet. But you can grab images for yourself and say, well, it's not as good, but that one is mine. That's fantastic. This is a part of the sky that I particularly like because it's quite colourful. This is the so-called Rho-Ophiuchi molecular cloud complex. This is part of the constellation of Scorpius, and that's a red giant called Antares. There's a globular star cluster there sitting right next door to it, Messier 4. And we can see a number of different features, including a triple star there called Rho-Ophiuchus, and that star is illuminating the nebula around it, and it's producing a polarization effect which tends to favour the blue light, and so these blue reflection nebula tend to come out blue, whereas the light that's being illuminated by the red giant Antares tends to come out a bit more yellow and orange. And so within the same frame you get these wonderful colour contrasts between yellowish and bluish, and you also notice that there are some dark clouds which are blocking the more distant light because these clouds are dense enough that the distant light from the stars is being absorbed before it gets to us. And I can't remember which particular molecules are present, but these cloud complexes are called molecular cloud complexes. There are some very complex molecules, not just carbon monoxide, but in some cases, you know, molecules like formaldehyde and other complex molecules within these structures. This particular image is taken of so-called Marcusons chain. Marcusons chain is a chain of galaxies. You can see these somewhat slightly fuzzy objects. Most of the objects here are stars, but you can see this chain of objects that are just slightly fuzzy, and these are a set of galaxies, and the more you look, the more you see. If you compare this with a star atlas, there are actually about 50 galaxies there, some of which are quite bright and some of which are quite faint. And these galaxies are linked by gravity. Some of them might be just foreground objects, but some of these are gravitationally bound into this complex stream of galaxies. When I took this, I looked it up and found that these galaxies were 50 million light years away. Again, I thought that was remarkable to be able to catch galaxies at a distance of 50 million light years just using a camera and a telephoto lens. But some years later it got me thinking, well, is 50 million light years the limit, or can you actually go further than that? And that's why when I had this idea of a lockdown challenge last year, some years after I took the image of Marcusons chain, I decided to mount my 300mm lens on a camera on this star tracker and point it at a patch of sky where I was hoping to catch a quasar, and right in the middle, I've told you about this before, but some of you might not have caught this, there where the red lines show is a quasar. And most of the light from the quasar has been focused into just 1 pixel. My camera happens to be 20 megapixels, but only about 1 pixel was actually used to catch the light of the quasar. And Marcarian's chain galaxies were 50 million light years away, but this beastie is 25 billion light years away. It's more distant by almost a factor of 1,000 or so. And that is about as much as you can expect any camera to do, because we're already looking back 90% of the age of the universe. We're already looking back 12.5 billion years into the past. Even the Hubble Space Telescope can't go beyond about 13.5. And again, that tells you the difference. With your own camera, you can go back 12.5 billion years for an extra billion years. To go from 12.5 to 13.5, that extra 10% takes you from an amateur camera to the Hubble Space Telescope. You have to go up by orders of magnitude in price to get a little bit extra in terms of percentage of going back further in time. So that was a lockdown challenge that I really did enjoy doing, and I was pretty gobsmacked the fact that it worked so well. What about going to Africa? Now, you don't have to go to Africa to enjoy the darkest skies, but I suggest if you're going anywhere, whether it be the UK or elsewhere in the world, on holiday or for any other reason, if you're interested in this, take a little star tracker with you and make the most of whatever dark skies you have. My friends and I have been interested in wildlife and in astronomy and in photography for many years. I fell into a bunch of people when I was at Birmingham University. We realised we had common interests in astronomy, and it turns out we also had interests in wildlife as well. And if you have interests in all of those things, then the natural way to go is to go on safari, because safari gives you wildlife and a pair of binoculars allows you to see lots of animals. Safari takes you to dark sky sites like the middle of Africa, where you have beautiful skies, and again you can use binoculars for looking at the night sky. And if you're interested in photography, then you have the overlap of photographing animals as well as astrophotography. So what's not to like? Basically, animals by day, stars by night, sleep when you get home. Okay, we did get a little bit of sleep while we were there, but the idea of putting all of these things together is a wonderful way of spending a holiday, and I'm really looking forward to going back to Africa when the pandemic allows, which could be a long time from now. So, I've told you about this particular tracker. On the right, you see the app that you can download for it, because what you need to know is, where is Polaris? Polaris isn't actually at the North Pole, it's slightly off the North Pole. So if you want to accurately line up your star tracker, you have to know where Polaris should be when you look through the polar alignment and look at this reticle. And this app, because it's an app on your phone, it knows where you are from the GPS, and it knows the time from the GPS. Therefore, it knows exactly where Polaris ought to be if you're lined up on the North Celestial Pole. And it tells you with a little dot, when you look through this polar scope, Polaris should be at that particular point where the green dot is. So you simply look through the scope and you adjust your tripod, or you adjust the little scale on the front, which basically tilts it to the right angle, and you adjust it until Polaris is where the app says it should be. In the UK, that is absolutely trivial and just takes a minute or two to put on the tripod, set up, and away you go. But if you go to East Africa, which is somewhere around here, and unfortunately right next door to the equator, the North Celestial Pole is of course directly above the Earth's geometric pole. In England, that's not a problem, you can see Polaris in the sky, but if you go to the equator, Polaris is effectively on the horizon and hidden behind elephants or hills or something else, and you can't really see the South Pole either. So you can't rely on lining up on Polaris. So that's a little bit of a pain trying to use a star tracker accurately in East Africa, and there are ways around that that I'm not going to go into, but it is still possible to use trackers on the equator. One of the satellite galaxies of the Milky Way is called the Magellanic Clouds, the Large and Small Magellanic Clouds. Here I took a picture of the Large Magellanic Cloud using an 85mm lens. There's not much colour in there because, again, this is a broadband source. It emits over the whole of the visible spectrum, so I just reduced this to black and white because there was essentially no colour information in it. Here's a chunk of sky for Peter. This is a bit of the southern sky. The stars down here are Alpha Centauri and Beta Centauri. It's nice to take a picture of Alpha Centauri just because everybody's heard of it. Everybody knows that's the nearest star. In this particular case, there's the Southern Crux. Next door is a nice little star cluster, and this dark region here is called this Coal-Sack Nebula. Again, it's a dark cloud which is blocking out some of the more distant stars behind it. Over on the right is a very unstable star which is emitting all sorts of matter. It's effectively shedding its outer envelope and producing this nebula. The star is called Eta Carinae, and this is the Eta Carina Nebula. And this is a definite candidate for a star that's due to go supernova before too long. Whether or not Betelgeuse gets there first, who knows? When it comes to looking at the Milky Way, you can just about see the Milky Way as long as you get away from light pollution within the UK. But it is staggering as to how bright the Milky Way is if you can get to a real dark sky site. Then you start to see all sorts of structure which is in the Milky Way because of the star clouds, because of the dust lanes, etc. And of course, when you can see that amount of detail, then if you take a long exposure image with a wide angle lens, then all of that detail starts to come out and you can start to pick out hints of colour as well. Different coloured stars as well as different colours within the Milky Way. This was a 35mm lens, and as you can probably see from the black corners, this was a mosaic where I've taken a few different images and then stitched them together afterwards when I got home, giving you a very wide-angle chunk of sky. To compare with what I took some years earlier, there's a similar chunk of sky. It's in the region of Scorpius. This one, the rectangle there, is taken with slide film, and you can perhaps see the constellation of Scorpion, but you can hardly see anything of the Milky Way itself compared to the enormous amount of detail you can see in the digital image. But there's so much going on there in the region of Sagittarius and Scorpius that you can hardly see the constellation itself. So if I actually point it out to you, then you can actually see there's Scorpius. And you do actually have to do this because in light polluted skies you see only the brightest stars, and with film you tend to only pick up the brightest stars, but with digital photography you can pick up so much detail, even the brightest stars sometimes get lost amongst all of the faint stars. In this particular image there's an awful lot going on as well as the Milky Way. There's Jupiter, there's Saturn. And it's nice to sit down with one of these images and to compare it again with a star atlas and just see how many nebula and how many star clusters are actually visible within the image. I haven't listed them all here, I haven't labelled them all. These are just the Messier objects. Charles Messier in the 18th century picked out all of the fuzzy looking objects which could in principle be confused with comets, and he started to catalogue them all. And here's just a small selection of some of the Messier objects that are visible in this particular image. It seems like there isn't anything interesting down in the bottom right-hand corner. That's not true. It's not a question of nothing interesting is going on. It's just that Messier from France could not see any further south than that line, and therefore he has not documented any of these objects. So all the Messier objects are north of that particular line. A couple of objects in there, M20 and M8, the so-called Lagoon Nebula, M8, and the Trifid Nebula, M20, I thought it might be interesting to try not a wide-angle shot of the entire Milky Way, but to switch to a telephoto lens and just see if I could image those. So I switched from a wide-angle lens to my favourite lens of choice for safaris, which is a 300mm lens. I used the 300mm and focused into that red rectangle, and then picked up M8 Lagoon and M20 Trifid Nebula. Again, you see predominantly pink because M8 is effectively a large cloud of hydrogen, and so it looks predominantly pink. But notice the trifid shows just a little more colour. If we blow that up a little bit, you'll see that the trifid, perhaps you can see that it gets its name from the fact that the pink thing here appears to have sort of three lobes, three petals of a flower, if you like. But again, the star further north than that tends to produce reflected light, which tends to produce a blue glow. So there's some light from hydrogen and there's some reflected light producing a blue light there. And again, you get this nice contrast between the blue and the pink. And it's a reminder that you can pick up some very nice detail using just a camera and lens on a star tracker. So you can tell that I'm a bit of an evangelist when it comes to this sort of thing. Some people I know spend enormous amount of money on telescopes and cameras and literally can spend tens of thousands of pounds over their lifetime on their hobby. And I've got no problem with them doing that. I've got a telescope in my back garden which cost me more than £1,000. But I must admit, over the last few years, I've obtained an enormous amount of satisfaction of just asking myself, what can I do with the camera I've already got and a relatively modest priced star tracker, whether it be one I built myself for £25 or whether it be one I bought for a couple of £100, what is it you can do with these beasties? And my personal suggestion is think about a compact one that you can take wherever you go, such that if you go somewhere with dark skies, you can make the most of your trip or your holiday whenever we're allowed to do that again. Thank you for listening.